So hello everyone, my name is Antoine Maiorca and I'm a PhD student at University of Mons in Belgium. And the work I will present here focuses on the objective evaluation metric for the motion generative models. So now generative models, especially prompt-based generative models, have become very, very popular in image generation or even text generation. I mean, everyone has heard of that model, even the non-initiated ones outside the academic and industrial world. So these have become very popular. But relating to motion generation, there are plenty of deep learning-based generative models that synthesize unseen and natural motion, human motion, in various contexts. For example, co-speech gestures, action generation, and so on. But now, one crucial question we all need to answer when developing generative models is how to assess them. How can I measure precisely what my model is able to do, is able to generate? So for assessing the performance of generative models, this is a challenging task actually, because we don't have access to ground truth data in a one-to-one comparison, So making an error measurement between ground truth data and generated motion data doesn't make any sense actually. So one popular way to assess that is by subjective large-scale user study. We gather people, we gather subjects, and they rate if they prefer such animation or another animation. But it takes time to do that, really. I mean, in an iterative process of developing a generative model, it really takes time. There is, among other things, a need for objective evaluation metric that can be applied fast and that can take all the samples that you generated instead of just, for example, cherry picking some stuff and then claiming that your model works well with the samples that you show to the subject, to the evaluators. So we use a statistical approach to just compare the distribution of the real data and the generated data. And one good candidate and very popular candidate for now is using the Fréchet distance that directly measures the quality of your produced animation and the diversity as well. Because one model that generates just one good sample, it's okay, but it doesn't make anything right. So basically, we estimate statistics on the distribution. So let's assume that PR and PG are the distribution of real and generated data. And we extract the mean and the covariance matrix, and we compute the Fréchet distance, which is just this formula with a trace of the covariance and the distance between the mean of the distribution. In image generation field, you might have known about the Fréchet inception distance, right? So this Fréchet inception distance, why it is collected, it's because for estimating distribution, we just gather feature maps, the last activation maps of the inception V3 image classifier. This is very popular to evaluate the image generative models, but actually it has inner bias that can occur in that evaluation and that leads to discrepancy between what we observe as human beings and what the objective metric measure. For example, in that slide, we have the Gaussian blurring. Oh, no, it doesn't work, sorry. We have the Gaussian blurring. When we increase the severity of the blurring, the Fréchet inception distance captures well that artifact. But when it comes to saturation of the image, it's very, very soft, the increase of the Fréchet distance. And some artifacts, it doesn't increase at all, so the Fréchet distance is not able to capture and assess correctly image dataset polluted by these artifacts. In motion, so what we have? Usually, action generation models are evaluated through STGCN, which is a model based on spatio-temporal graph convolutional neural network. And we just estimate the statistics on the distribution on these feature maps. But we need to train the model. It means that if this is an action classifier, we need a labeled dataset with a label, with action. But that does not cover all the things in motion generation. For example, co-speech gestures, we don't have label. We just have motion associated to speech, to text or speech. So that's why convolutional-based autoencoders have been proposed to extract the latent space and estimate statistics on this latent space. The statistics is the mean and the covariance matrices. Now, the problematic we want to cover during this talk is the Fréchet distance based on autoencoder, is this sensitive to common motion artifacts? So we'll define foot skating over smoothing, and is it correlated with human perception? So with user studies, subjective user studies. And finally, we propose a transformer-based autoencoder instead of convolutional one-dimension-based autoencoder, because we measure that this is more robust to the convolutional one. So, what's foot skating? One of common motion artifacts. This is the fact that the foot slides when it is in contact with the ground, which is an unnatural behavior, right? We observe and we measure that taking an animation model from mixture of experts, well-known animation model with mixture of experts, we decrease the hidden size of the model, and so we reduce the number of its parameters, and when we do that, we increase the foot skating on the locomotion of the dog. So this is a nice approach to induce foot skating in our animation, okay? So we use the hidden size of 512 neurons, 256 neurons, and 64 neurons. And reducing the hidden size, it increases foot skating. Now, over smoothing, this is the fact that we remove the high frequency component of the motion, but the frequency that are important in what we perceive in the motion natural. This is the small variations in the Cartesian position of the joints, for example, or on the rotation. And this is very important, for example, in expressive gestures where every variance of motion of the limbs is important. So we just smooth the motion, and if we increase the smoothing factor, defined by zeta parameters here, so 5, 25, the motion becomes more and more static. Okay, so this is also a way to reduce the diversity in the dataset. So our approach, we have the real motions and the synthetic motion, but the synthetic motion is the real motion polluted by the noise, right? By the artifact we defined later. We use the embedding network to extract the latent space, and we measure the distribution. We measure the distance between the two distributions in the latent space. So the question here is, what's the embedding network? We have convolutional-based autoencoders. Now we propose a transformer-based autoencoder. So instead of having the convolutional layers, we have self-attention layers that are able to make the latent space Z in the encoder part. Okay, so this is trained. This is trained by reconstructing the motion M at the input, and the output motion is Y. That is basically the one-to-one relationship between them. Okay. Now, we have two datasets here with different motion features and different skeleton. We have the dog locomotion, when we have the velocity profile, rotation and stuff. And we also have the motion from Genea challenge. Some of you may know that this is a challenge that gather people that are interested in expressive gesture generation from speech. And so there are some of teams that are participate to that challenge and they submitted motion related to speech. And so the motion are output from them, their generative models they submitted. This is very important because this is annotated by users. Okay, so we have already the subjective evaluation that has been done. So we can measure the correlation between the human perception and our metric defined by the transformer autoencoder, right? And we test it for different motion length. So we just make samples of motion from 15 frames to 60 frames. Okay. So the results are, considering motion reconstruction, the transformer outperformed the convolutional-based approach. So the red is from transformer and the blue color is for the convolutional autoencoders. And you can see that at each motion length, that's the pattern repeats itself. And I mean, the transformer-based is more powerful than the convolutional in terms of motion reconstruction. Now, what about Fréchet distance? On the x-axis, you have the number of parameters inside the hidden size of the motion animation model. So remember, when we shrink the model, the foot skating increases, okay? And I didn't say that, but it's very important as well. The Fréchet distance, the lower, the better, because it's the distance between distribution, right? And so for the transformer-based approach, considering every motion frame, we have the nice patterns of the Fréchet distance decreasing with the Fréchet distance decreasing when we increase the number of parameters of the model. So when there is less foot skating, which is a nice, which is the expected behavior, the Fréchet distance can measure efficiently, even with the convolutional autoencoder, the foot skating artifacts. But what you observe is that the convolutional, the score given for convolutional layers are more spread into the space of the Fréchet distance. In the transformer layer based, the motion length does not influence a lot on the value of the Fréchet distance. It can be very important if we want to evaluate motion datasets that have different length, right? So considering smoothing over smoothing, so we just apply the filtering on the motion, the Gaussian filtering, and what we observe is that increasing the smoothing factors, zeta, the Fréchet distance on the y-axis increases. That means that when the motion is less natural, is more and more static, the Fréchet distance increases, which is important. And once again, we can see the repeating pattern here about the convolutional-based evaluation is that the value of the Fréchet distance is more spread when it comes to evaluate different motion length. Okay, so the number of frames is crucial for the convolutional approach, but not for less for the transformer autoencoders, knowing the number of frames for evaluating. Okay, now what about the human judgment correlation? The correlation between the score and the human judgment. So what you need to understand on this slide, on this table, is that here you have the submitted motion samples from the team of the Generative challenge. You have the score given by the users. So is it a nice motion? Is it not nice motion, basically? And you have the score given by the objective metric in each tested configuration. So in every motion frame and in every model used, okay? And now we will compute the Kendall rank correlation between those data, right? And what we observe is that here on the x-axis you have the motion length, on the y-axis you have the Kendall rank correlation in absolute value, because once again, Fréchet distance, the lower the better, and the median user rates were in increasing order. Yeah, you have two datasets, the upper body gestures and the full body gestures, submitted by the team. And what we observe is that for the convolutional autoencoder, even when there is a small variation in the frames, the correlations are very different. The rank correlation is very different, but this is more stable in our transformer-based approach. And what we need to know on the slides as well is that the value on each point is the p-value of the correlation. So keep in mind that we had a few data. So this is basically sometimes not statistically significant, but we believe that this can be improved by using more and more data like that and more evaluation. Yes, so once again, we see this repeating pattern about the Fréchet distance being more stable across the number of frames when we evaluate, even with the human judgment. So we have, in conclusion, we have the proposed transformer can lead to a more stable Fréchet distance across the number of frames. So we could, there is a need for more analysis, but we could actually evaluate motion dataset with different length because it's stable across that features. Yes, so pretty short presentation. Feel free to contact me with my email here, and thank you for listening.